Něco. Okay. Hello. Good day, everybody. My name is Tomáš Votroubek, and I would like to tell you about our result in robotics. So, solutions for inverse kinematics using branch and bound. We wrote this with Tomáš Kroupa, who happens to be a member of the committee, but don't let that worry you. Inverse kinematics is the task of computing control parameters, which bring a robot into a desired configuration uh, in its kinematic constraints. For us, we're interested in manipulators made up of revolute joints, where given a position and orientation for the end effector, your task is to compute the individual joint angles. I'm going to do it like this to get it there. Now, for a class of so-called redundant manipulators, which are, for simplicity, manipulators which have more joints than strictly necessary by the problem, there are going to be infinitely many configurations satisfying such a post constraint. For this reason, we give the user option to specify their preference function over feasible configurations. One preference function which is interesting to roboticians would be manipulability, which is kind of the ability of a manipulator to move after reaching its desired pose. You could then optimize for speed or strength in some direction. Now we went with something slightly different, inspired by iCap, which is this robot, which, if you imagine the situation as a humanoid robot, which is trying to reach for an object, in which case you are likely to include parts of the torso in the kinematic chain just to get sufficient range of motion, you would presumably prefer the solution where the robot doesn't just bend over for no reason. Even though it does increase the manipulability, the upright solution may look more human. The general version of this is just an angular distance from some preset vector of angles. This is what ICAP does. We just formulate it like this, just a weighted difference. If you put all of the weight on the first joint, you could definitely encode the verticality of the torso. Otherwise, you could use it, for example, if you encode the current angles of the joints, then you could be minimizing the movement in the space of joints. Now, we like to solve things using mathematical optimization, and so I'm going to build up the program to do that. We already have the objective, that's just the user preference function. We're going to need the pose constraints, which is done through what is known as Denavit-Hartenberg matrices. They look more complicated than they are. The only variable is the joint angle, and it works in a way where each joint is going to induce some transformation in the coordinate system. So if you want to go from the coordinate system of the end effector back to the coordinate system of the base, you just multiply all of the transformations induced by the individual joints. Then you formulate your desired transformation in the coordinate system of the base for the end effector, the position and orientation as a transformation matrix, and you equate the two sides. The actual transformation induced by the manipulator and the desired one. So we add this as a constraint, and really the only thing that we need now is some inherent constraints of the manipulator. For humanoids, there's definitely going to be constraint on the range of motion of the joints. Specifically for ICAP, there should also be a linear constraint for the length of its tendons, just so it doesn't move in a configuration where it could tear its tendons apart. Now, the Cartesian solver for ICAP doesn't do this, so we ignore it as well and just stick with this generic formulation. Now, we could actually try and solve this if we just apply a nonlinear solver with just one small change. Instead of torturing a nonlinear solver with 12 nonlinear qualities, we just put this in some notion of a norm. It could be squared, it could be whatever, just to simplify the constraint. And it turns out that this sometimes gives reasonable results. In fact, for ICAP, it gives results more often than not. But you don't get any guarantees if you apply a nonlinear local solver such as IPOpt. Right, but the reason I'm telling you this is because we use this as a heuristic to warm start our actual solution. Now, we are not the only ones to notice that this works. In fact, ICAP uses pretty much the same technique to do this. They simplify it even more just to get a higher percentage of successful solves, where instead of just satisfying the position exactly, they solve it within some epsilon, and the rotation, they just put that inside the objective and kind of hope for the best. Right, but this is kind of what it takes to solve for humanoid robots. If you want to solve them in real time, you don't get any guarantees, but it is fast. There are other methods to solve robots in real time, but again, you either don't get guarantees or it's not generic. So it's specific to some manipulator designs or you don't get guarantees. Now, there is research into this field of getting globally optimal solutions. Two pertinent ones are from Dai, who tries to approximate the feasible region, who tries to construct outer approximations of the feasible region, such that he can then give you a certificate if the pose is infeasible. But if the pose is feasible, he can only give you an approximation. But at least he can give you a certificate if a pose cannot be achieved. Now, even more relevant than that is a paper by Trutman and Paidla, which our paper is a follow-up to, who tries to approach this problem using polynomial optimization, Lassay hierarchies, and Grosvenor bases. Now, this is currently limited to 7 degrees of freedom, even though Paidla would tell you that it technically isn't. But I'm going to show you a method that actually isn't, which is based on spatial branch and bound. Now, spatial branch and bound is branch and bound like any other. Well, let's imagine that you're trying to optimize y, so trying to minimize y, such that it lies above the red concave quadratics. What you would do in every branch, you would have some range for, let's say in this case, the only variable x. What you could try and do in every branch is try and find, let's say, a local solution, which would then give you an upper bound. You could use a local solver, you could use an intersection with the boundaries or something like that. At the same time, you would construct convex relaxations of each constraint individually, which in our case would give you a linear program, and solving that would give you a lower bound on the objective. So in each branch, you would have a possibility to get an upper bound, and you would definitely get a lower bound. Then you would split the feasible region, in this case of the only variable, let's say in half, and you would repeat the process. You would continue this until, well, good things can happen. So for example, in this case, the last branch, the solution of the last branch, the feasible solution in this last branch is actually better than the even the relaxed solution in these first two branches. So you could prune them, right? But you continue this approach until the upper bound and lower bound gets close enough within some epsilon, and then you declare that to be the solution. Now, this is kind of predicated, first of all, on being able to find feasible solutions, which is why I talked about the heuristic before, using linear programming, nonlinear programming, and also in being able to construct the linear or convex relaxations. Now, there exist many relaxations for many different things, so from fractions, exponentiation, piecewise linear things, trigonometry, and stuff like that. But multivariate things can be a problem. And if you look at our program, the objective is just piecewise linear. That's definitely not a problem. The range of motion constraint is just a box constraint that's also linear. That's not a problem. But the pose constraint is going to be very nonlinear. So even just the single matrices depend on again, the only variable here is the theta, the joint angle. And it comes into the matrix using the sine of theta and cosine of theta. Now we can simplify this a little bit just by pulling those variables out as the Cartesian variables, so Ci for the cosine of theta, Si for the sine of theta. These constraints are not a problem for spatial branch and bound. And now the matrix is simplified to the point where the elements of the matrix are now linear in S and C. And so a product of matrices which are element-wise linear would be element-wise multilinear. And that's again a multivariate thing, so it would be a problem. However, we can use an idea from 40 years ago, which is just a change of variable. So to try to project the problem into a higher dimension where it would be easier to describe. So as a concrete example, if we take the multilinear constraint x times y times z times w equals 0, we just introduce a new variable alpha1, which is equal to x times y. And then the constraint is alpha1 times z times w. We continue like this, simplifying the original constraint until that is linear, and we get a new set of bilinear constraints. It turns out those are not a problem, and again, we've known how to solve these for 50 years. We have tight convex envelopes in four planes. Now we can actually do this lifting process directly on polynomials. That could be as simple as just considering each monomial separately. So you just keep pulling out bilinear things. In fact, this will kind of work for anything constructed of binary operations, as long as you have relaxations for those functions. And we can actually do this directly on matrices. So since the matrices are element-wise linear, if you just take the product of two matrices, you can introduce a new matrix variable and just equate the product of two matrices with a new matrix variable. And that turns out to be the fastest formulation. So I'm going to show you how to do this concretely. If we have the post constraint, that's the second line, which is going to be transformation of the first joint times the second joint times the third joint. You pull out the first two transformations, introduce a new matrix variable, and again, as before, you just keep simplifying this post constraint until that becomes linear, and you get these new sets of constraints induced by the matrix variable, so 12 constraints for each matrix variable. And while this seems to be heading in a kind of a ridiculous direction, it kind of gets worse when you realize that spatial branch and bound is exponential in the number of variables. And we convert a program which originally has, let's say, 10 joints, so 10 variables, into one which is now going to have 190. But it turns out this is not a problem. And if we look at the results, if I compare it to the previous method, which is the sum of squares Lasser hierarchy-based method, what used to take for the sum of squares, let's say an hour or 2 hours in their paper, we can now do in about 12 seconds. Now, based on the fact that I had to use a logarithmic scale just to get the two methods on the same slide, you probably know that this is not quite a fair comparison, and it isn't, because most of the time is actually taken up by the Grosvenor basis computation. And they did that in a quite a, let's say, naive way. There is a way to do this faster. I'm not going to explain the way, but I'm just going to say, yeah, if you compared just the two methods, it would be roughly comparable, let's say. Instead of 12 seconds, it could be 18 seconds. The problem would be about 50% failure rate. But it would be more comparable, right? However, if I'm going to skip this. Let's say I have a better method for constructing the Grosvenor basis, which just involves pre-computing the number of polynomials that I need. I can get the Grosvenor basis computation done instead of an hour in about 48 seconds. So at this point, I have a new reduced system, and I can again use both of the methods, so spatial branch and bound or Lasser hierarchies. And in this case, it's more comparable. So we solve it on average, let's say, in a second, and Lasser hierarchies would solve it in about 5. So that's that's closer to the actual speed up. Now I have similar results for other manipulators, for KUKA, which happens to just be a simple manipulator. Again, the result is about the same, in this case about 10 times faster. I've also experimented with other objectives. So if you just solve towards some objective, you don't care which, and you just stop as soon as you find the first feasible solution, it turns out that you can solve for the ICAP in about 20 times a second. This is not quite this is, again, not quite a fair way of saying it. No, I don't measure the startup. So this is just a result of IPOpt being able to find feasible solutions very often. Or if it doesn't find a feasible solution, Gurobi can then, during pre-solve, convert that into a feasible solution. So there should be about, let's say, 1/10 of a second, or however fast IPOpt can find solution, or your heuristic can find an initial solution. And this extends even to 10 degrees of freedom, which is a new result that definitely wasn't possible before. And again, feasible solution can be found in about a second. Okay, so just a summary. This is applicable to all manipulators. That's the big feature of it. It can find solutions with micrometer precision. If a solution exists, it will find it. It will find a globally optimal one. If it doesn't, it will tell you certainly doesn't exist a solution. And it extends at least up to 10 degrees of freedom. And most importantly, it's open source, so please try it. By all rights, this shouldn't work. So if you have any way of disproving the results, if you have any extensions or anything like that, I would like to hear it. So thank you for your attention.
Okay, any questions? You don't have any questions?
Thank you for the presentation. So you at one point said that it generates exponentially, is exponentially complicated in number of constraints, and then you said it didn't...
Variables.
Variables, right? Sorry. And then you said it didn't matter.
Mm-hmm.
And I didn't quite get why. Can you
Nobody
elaborate on
does.
that?
Nobody knows why. It just turns out that somehow the problem is a lot simpler than it looks. So it's I should have said it this way. So spatial branch and bound is worst case exponential. It doesn't say anything about the expected runtime, right? And in this case, it turns out to be a simpler problem than it looks.
Kuba?
So this is more like a comment. So I think that you would like to really see the breakdown of the runtime into the number of the nodes in the branch and bound tree visited, which would be very small, the time spent in the cut generation heuristics, the separation of the cuts, and the time spent in the primal heuristics. And really, like the magic is the combination of the three. So sort of you have the primal heuristic, which finds the actual solution, which is very close to optimality very fast. Then you can prune much of the tree, and then you can introduce some valid violated inequalities, which is known as cuts, and that sort of reduces the number of the nodes visited to very little. So the real magic is that the number of nodes of the branch and bound tree you visit will be very small. I don't know whether Tomáš has some exact numbers on this.
I don't. I know somebody asked me last time, and it turns out not to be
It's, I
surprising.
think, useful, right? Precisely for explaining why this is fast and for making this like I don't know, more believable or credible.
I tried a lot of different things which should have made it slower, such as turning off the pre-solve and turning off the heuristics inside Groby. It turned out not to make really much of a difference.
Yeah, but right. So sort of the number of the nodes visited in the branch and bound tree is still like a key
So I could
measure
say
of performance that I think would be good to list.
I could answer it in a different way. So, for example, the results of Skip, which is the open source solver for the same problem class, has roughly the same number of nodes. That's what I remember. I don't remember the exact number, but has roughly the same amount of nodes. But it is comparable to the Lassai hierarchy, so it's a lot slower. So it's not just about the number of nodes.
No. It's the heuristics. It's
Even if
number
you
of
turn them
things.
off.
Second.
Even if you turn the heuristics off in Gurobi, and even if you use two different solvers which have roughly the same amount of nodes, Gurobi turns out to be a lot faster than Skip. I think it's partly the linear programming performance, partly how it selects the branches, but it shouldn't have the same number of nodes. So it's kind of a surprising result.
Any other questions? Stefan?
This is more about the impact of what you have shown us, just to judge it. Would it like this industrial robot arms, they are used all over the place in industry for decades. Will they, like KUKA and so on, will they, or have they already indicated that they will use your solution if it's like 10 times faster? It may help them a lot, or?
For these industrial robots, definitely not. So KUKA is designed around the problem around the idea of this being a hard problem. So they just make a robot that is easier to solve for. They construct it in such a way that it's constructed of 3 sequences of 3 consecutive joints, which all intersect at a single point, and that turns out to be simple to solve in closed form. So they just design the manipulator around this problem. So they would definitely not use something like this, unless they want some robot that is more powerful or something like that, in which case they would have to drop that constraint. In that case, this could help them. So this is more of the impact. So it could be useful for manipulator design. Rather than trying to solve for existing robots, this is more for inventing better ones.
And the idea of this humanoid robot, is the problem there more prominent than in the industrial setting?
I don't know. I don't know if they are going to use it. I think the story I heard is that they are just kind of sufficiently happy if they get a solution, and global optimality for humanoids is not that important. But it might turn out, I don't know, if it saves energy or something like that. If you minimize the movement in joint space, it could save energy. That's a possibility. But we would have to make it faster to make it real time. So I still see the result more in the field of manipulator design than real-time inverse kinematics.
Any other questions? Vilo?
So Pernia will hate me for this, but it looks like it's a Julia library.
Oh,
Do
yes.
you think that the adoption potential by the humanoid robots and so on can be somehow lower because of that, or are you trying, or do you have a version for
This is
more prevalent languages as well?
He looks like he hates
so
it
the
right now, yes.
implementation. The implementation contains a WebSocket server, so they shouldn't have a problem connecting it with whatever they have. You just send the matrix. I made it in the most simple way. You just send the matrix in as a series of ASCII characters, so any language should be able to communicate with it. But this is just a proof of concept. In the runtimes that I measured, I didn't include the overhead of Julia, which is quite massive. So. Uh, okay.